So yesterday we saw that a logarithm is an inverse of an exponential. Remember, to do the inverse, if you're talking about the equation, you switch the x and y around and then solve for y. If you have a table of values, you switch the x and y values around. The domain of the relation is the range of the inverse and vice versa. So this first question says to state the inverse of f at x equals 3 to the x. So instead of f at x equals, we'll write it as y equals 3 to the x, because our first step to write the equation of the inverse is to interchange x and y. So now we have x equals 3 to the power y. But we want to write this in the form y equals. And there's nothing we can do. We can't divide both sides by y or take the y root of both sides to get y by itself. It doesn't work that way. So what we can do, though, is change it from exponential to logarithmic. Remember that the exponential function has a base. When you convert it into a logarithmic function, the bases are the same. This exponential function has a base of 3. So when we write it as a log, it'll be log base 3. And make sure you write that 3 down as a subscript. It's got to be down low to make sure that we know it's a base. And to get the order that the other pieces go in, like we saw yesterday, we'll start with the base and cycle through. So after the base of 3 comes the letter x equals y. When you start with the base and cycle through, it tells you the order that the other pieces are written in. And now we have the equation with y by itself. That equation is the same equation as x equals 3 to the y. It's just in a different form. X equals 3 to the y is an exponential function. You can change every exponential function into a logarithm. And that's what we did. And so now we have y by itself. Y equals log base 3 of x. Now, it says sketch the graph of the inverse, identify those characteristics. So I think probably the easiest way to do this is do a table of values for the original function, y equals 3 to the x. Let's do a table of values for that. And then to get the corresponding table of values for the inverse, which is what the equation we ended up with is, we just switch the x and y values around. But I'm going to start with a table of values for the original relation, y equals 3 to the x. So these are the values for x I'm going to choose. When x is negative 2, 3 to the negative 2 is 1 over 3 squared, or 1 over 9. When x is negative 1, 3 to the negative 1 is 1 over 3 to the positive 1, or 1/3. When x is 0, anything to the power of 0 is 1. 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27. Now we might not have room for all these points on our graph, but that's okay. To get our points for the inverse, we'll just switch the x and y values around. Instead of negative 2 comma 1/9, we'll have 1/9 comma negative 2. Instead of negative 1 comma 1/3, we'll have 1/3 comma negative 1. Instead of 0 comma 1, we'll have 1 comma 0. Instead of 1 comma 3, we'll have 3 comma 1. And instead of 2 comma 9, we'd have 9 comma 2. And that'll be the last point that I'll do because I don't have room for a value of 27 on this graph. We saw yesterday what the graph of a logarithmic function looks like. It has the y-axis as a vertical asymptote. And the only thing that might change that would be if the graph was moved, shifted left or right. That would change that vertical asymptote. And we're going to get to that. We're going to do transformations of logarithmic functions. But we're not there yet. So if I put my points on here, I've got the points 1/9, comma, -2. I've got the point 1/3, comma, -1, 1, comma, 0, 3, comma, 1, and 9, comma, 2 would be approximately right there. Again, the y-axis is a vertical asymptote. So that's what the graph of that logarithmic function looks like. So the domain of this is x is greater than 0. So we can go from 0 to positive infinity. X is the argument of that equation. The equation is y equals log base 3 of x. X is the argument, it's what you're taking the log of. So what this tells us, and we talked a little bit about this yesterday, this tells us you cannot take the log of a negative number, because our domain is that x, which is the argument, must be greater than 0. If you try it on your calculator, you take the log of, say, -10. Whoops. Log -10. You get an error. It doesn't exist. You cannot take the log of a negative number. Okay? And that's our domain. Our range in this case would be all real numbers. This graph goes up and down forever, from negative infinity to positive infinity. There is an x-intercept. Our x-intercept is at the point 1, comma, 0. There is no y-intercept because the y-axis is a vertical asymptote. And the equation of that asymptote would be the line x equals 0. It's an equation, so it's got to have an equal sign. It's got to have a variable. If we change the argument or we change the base, that's going to change the steepness of the graph. That's what it's going to change. Okay? So if you have a logarithmic function that hasn't been transformed in any way, the y-axis will always be an asymptote. The only thing that would change that again is if the graph was shifted left or right. Then that'll change the vertical asymptote. All right, so question A on the next page asks us to write the inverse of that. So like we did on the last one, we'd start by writing the equation only in terms of y instead of f at x. To write the inverse, we interchange x and y. And technically this is the equation of the inverse, but we always want to have it so that y is by itself. And to do that, we convert from exponential to logarithmic. It's the same equation, just in a different form. We've already interchanged x and y. That's our first step to get the inverse. This exponential function has a base of 1/2, so that'll be the base of the log. And to get what order the other pieces go in, start with the base, cycle through. After the log of 1/2, the next thing that comes after that is the x, and after the x, you have your equal sign, and then the y. Y equals log base 1/2 of x. That is the equation of that same equation, only we changed it from exponential to logarithmic. And by doing that, we now have y by itself. It is the same equation as this exponential function that we wrote after we interchanged x and y. We did that because that's the first step to write the equation of the inverse. Those two equations are the same. They're just in different form. That's all. They're just in different form. So again, it asks us to sketch the graph of f at x and its inverse. So this one asks us to do both. I don't think the last one did. No, it just said the graph of the inverse. So we're going to sketch them both, and we'll start with a table of values for the original function, the exponential function. I'm going to choose these values of x. 1/2 to the negative 2 would be 2 over 1 to the positive 2 squared, which is 4. 1/2 to the negative 1 will be 2 over 1 to the positive 1, which is 2. Anything to the 0 is 1. 1/2 to the power 1 is 1/2. 1/2 all squared is 1/4. This is a decreasing function because the base is between 0 and 1. We have the points negative 2, comma 4, negative 1, comma 2, 0, comma 1, 1, comma 1/2, 2, comma 1/4. This is an exponential function. An exponential function has the x-axis as an asymptote, unless the graph has been shifted up or down. So that's the graph of the original function. Now, the graph of the inverse. I can take the points on the original and just switch them around. Instead of negative 2, comma 4, it'll be 4, comma negative 2. Instead of negative 1, comma 2, it'll be 2, comma negative 1. Instead of 0, comma 1, it'll be 1, comma 0. Instead of 1, comma 1/2, it'll be 1/2, comma 1. And instead of 2, comma 1/4, it'll be 1/4, comma 2. 4, comma negative 2, 2, comma negative 1, 1, comma 0, 1/2, comma 1, and 1/4, comma 2. This is what the graph of that logarithmic function looks like. Again, because the base is 1/2, it is a decreasing function. And it's maybe a little difficult to see that, but once again, remember that a graph of a function and its inverse are reflections about the line y equals x. So that goes through the point negative 4, comma negative 4, negative 2, comma negative 2, 0, comma 0, 4, comma 4, etc. These two graphs are reflections about that line. Not real easy to see that, but they are. Okay. What would happen is that this piece up here would reflect to that piece there. And these two pieces reflect over the line y equals x. But we don't need to rely on that to sketch our graph, because we can generate points for the original relation and then switch them around to get the points on the inverse. So if we write these characteristics of the logarithmic function, the inverse graph, the domain, once again, the y-axis is a vertical asymptote. This graph is on the complete right side of the y-axis because you cannot take the log of a negative number. X is the argument. It's what you've taken the log of. Yeah, the base changes, but you're taking the log of x, and you cannot take the log of a negative number. So the domain is still from 0 to positive infinity. The range, it still goes up and down forever. There is an x-intercept. It's the point 1 comma 0, but there is no y-intercept because the y-axis is a vertical asymptote. And the y-axis is our vertical asymptote. The equation of that is the line x equals 0. It's an equation. It's got to have an equal sign. It's got to have a variable. If you just write 0, that's not correct. It's got to be an equation. And the equation has to have a variable. It says, without technology, estimate the value of log base 2 of 14. Well, as we saw yesterday, if you want to find the value of a log, one thing you can do is set it equal to x. And then, what does this mean? Well, if you convert from logarithmic to exponential, start with the base and cycle through. Remember that in either format, the bases are the same. The log has a base of 2, so the exponential function will have a base of 2. After the 2 comes the power x. After that comes equals 14. So this is asking us 2 to what power is 14. So we can do that without technology, but after that, it's kind of difficult to even estimate what the answer is to one decimal place without technology. Okay, so one thing we could do, and we'd have to use our calculator to do this, is do a guess and check, a trial and error. We know that 2 cubed is 8, and 2 to the 4th is 16. So x has to be between 3 and 4. Probably closer to 4 than it is to 3, because this 14 is closer to 16 than it is to 8. So again, x will be closer to 4 than it will be to 3. So if we went 2 to the power 3.6, not 14, obviously, not greater than 14, less than 14. But if we went 2 to the power 3.7, closer, but let's see if we can go higher. 2 to the power 3.8. That's probably as close to 14 we're going to get without going over, like 13.9. If we do 2 to the power 3.9, that's further away from 14 than the last one we did. So using technology to guess and check, we can say x is approximately 3.8. Approximately. And then same thing for this next one, estimate the value of log base 3 of 50. So if we want to know what that is, let's let it equal x. This log has a base of 3, so we write it in exponential form. It'll have a base of 3. To get the order the other pieces go in, start with the base and cycle through. 3 to the power x equals 50. So that's what log base 3 of 50 really means. It means 3 to what power equals 50. Now 3 cubed is 27. 3 to the 4th is 81. So it's going to be somewhere between 3 and 4. Okay. 50 is a little closer to 27 than it is to 81. So our answer is probably going to be closer to 3 than it is to 4. If we try 3 to the power 3.2, 3 to the power 3.3, 3 to the power 3.4. So we're getting there, but we're still not there. We're approximately 8 numbers away. What if we try 3 to the power 3.5? Even closer, 3 to the power 3.6. That's as close as we're going to get. So approximately 3.6 would be our answer. Oops. to 1 decimal place. So we said at the start that there's some applications of logarithms, and one of those applications has to do with the Richter scale. So that was invented in 1935 by this American seismologist, Charles Richter. Developed a scale formula for measuring the magnitude of earthquakes. The Richter magnitude M of an earthquake is defined as, so M is the magnitude, it's defined as a logarithm. The log of A over A sub 0, where A is the amplitude of the ground motion, usually in microns, measured by a sensitive seismometer. A sub 0 is the amplitude corrected for the distance to the actual earthquake that would be expected for a standard earthquake. So that's what those values represent. In 1946, an earthquake struck Vancouver Island off the coast of BC. It had an amplitude of, or that was, 10 to the 7.3 times A sub 0. What was the earthquake's magnitude on the Richter scale? So we have that formula above, that M, the magnitude, is log of A over A sub 0. Magnitude is log of A over A sub 0. And for this question, it says the amplitude, which is what A is, was 10 to the 7.3 times A sub 0. So it'll be the log of A, the amplitude, which we are told was 10 to the 7.3 times A sub 0 over A sub 0. Notice that in this case, there is no base for that log. Right? The original equation, there was no base, which means it's a common log, or base 10. And the A sub zeros cancel here. So we're left with the log of 10 to the power 7.3. Which, because it's a common log, we can evaluate this in our calculator. The log of 10 to the power 7.3 equals actually 7.3. And yesterday we talked about a couple facts about logarithms, and this was one of them. If the base of the log equals the base of the argument, when the argument is written as a power like this is, the argument is what you're taking the log of. You're taking the log of 10 to the 7.3. So when the argument is written as an exponent, and the base of the log equals the base of the argument, the answer is just the exponent. We talked about that yesterday when we went through some of the facts about logarithms. Let's go back and see if I can find that. I think it was here. No. Yeah, this one here. That was that one right there. If you have a log of an exponential, the argument is an exponent, and the base of the log equals the base of the exponent, the answer is just the exponent. And as we get into the laws of logarithms, we'll see another reason why this is true. Okay? So, that's the magnitude of that earthquake, 7.3 on the Richter scale. Question B, the strongest recorded earthquake in Canada struck Haida Gwaii off the coast of BC. So that used to be the Queen Charlotte Islands. It's north of Vancouver Island. In 1949, it had a Richter reading of 8.1. How many times as great as A sub 0 was its amplitude? So we're going to start with that same equation. M, the magnitude, is the log of A over A sub 0. And in this case, we're told that the Richter reading, which is the magnitude, is 8.1. So 8.1 will equal log of A over A sub 0. This question wants us to know or find out how many times as great as A sub 0 was its amplitude. Essentially, we want to get A by itself. That's what we want to do. Get A in terms of A sub 0. So to do that, keep in mind that this is a common log, a log with a base of 10. We're going to convert from logarithmic to exponential by starting with the base and cycling through. Remember that when you convert from one to the other, the bases are always the same. This log has a base of 10, so as an exponential function, the base will be 10. To get the order that the other pieces go in, we start with the base and cycle through. And remember, whenever you cycle through, you're always crossing that equal sign. So after the 10 comes the 8.1. It's 10 to the 8.1 equals A over A sub 0. And remember, we wanted to get A by itself. We want to know how many times as great as A sub 0 is, A the amplitude. So we would get A by itself by multiplying both sides by A sub 0. A the amplitude is 10 to the 8.1 times A sub 0. So that is the scale factor, how much greater A is compared to A sub 0 as an exact value. We can find out what it is by going 10 to the power 8.1. It's going to be a big number. 125,892,541.2 times. So quite a bit bigger. All right, question C says, compare the seismic shaking of the two earthquakes. So compare them. You know, how much greater is one magnitude compared to the other? That's what we want to do. The seismic shaking is the magnitude. So we're going to do the amplitude of the Haida Gwaii quake, which was the larger one. And we'll divide it by the amplitude of the Vancouver Island quake. Now, if we look back at this last part that we did, part B, let me just circle the part that we're looking at. We're comparing these two amplitudes of these two earthquakes. We're dividing the one amplitude by the other. We saw in part B that we did some math to get A by itself. The amplitude of that earthquake was 10 to the power 8.1 times A sub 0. That's the amplitude of the Haida Gwaii quake. And where the 8.1 came from, it was the magnitude of that earthquake. That's the Richter reading. So we can do the same thing for the Vancouver Island earthquake. it had a magnitude of 10 to the 7.3 times a, or I should say it had a magnitude of 7.3, and so the amplitude of it would be 10 to the power 7.3 times a sub 0. And those are the two things that we're going to divide to see how many times more intense the Haida Gwaii quake was compared to the Vancouver Island quake. So when we divide these, the a sub zeros cancel, and you're left with dividing powers with the same base. When you divide powers with the same base, you subtract the exponents and keep the base the same. It'll be 10 to the power 8.1 minus 7.3, or 10 to the power 0.8. And 10 to the power 0.8 is approximately 6.31 times as intense. Okay? And on the next page, the largest measured earthquake struck Chile in 1960. It measured 9.5 on the Richter scale. How many times as great was the seismic shaking of the Chilean earthquake compared to the 1949 Haida Gwaii earthquake, which measured 8.1 on the Richter scale? So this is exactly the same as the one that we just did, where you're going to divide the amplitudes of the two, so to see how many times greater one is compared to the other. We're going to take the amplitude of the Chile quake that's the one that's greater, and divide it by the amplitude of the Haida Gwaii quake. And as we saw in the last question, an expression for the amplitude is 10 to the power of whatever the magnitude is times a sub 0. The Chilean quake had a magnitude of 9.5 on the Richter scale. So it'll be 10 to the power 9.5 times a sub 0. Divided by the Haida Gwaii quake, which measured 8.1 on the Richter scale. So it'll be 10 to the 8.1 times a sub 0. And we're dividing these two. A sub zeros cancel. And we're dividing powers with the same base, so you subtract the exponents and keep the base the same. So it's 10 to the power 9.5 minus 8.1, or 10 to the power 1.4. Which, if we use our calculator to see what that is as an actual numerical value, it's approximately 25.12 times more intense. 25.12. Okay? So on page 380, 381, you can work on questions 8, 9, 14, and 21. I will post those solutions to Google Classroom so you can check your work. And again, this practice is important. So if you see questions like this on a quiz or a test, you've had a little bit of work with them. Okay?